Log on, tune in, find out. Another good idea from Cambridge.
First speaker, an old friend of us, Weizhu Bao, and yeah, he's going to speak about compressed vortex fertility.
Thank you. Okay, so first I'd like to thank my good friends Peter Markovich, Shijin, and Jose, who is not here, for the kind invitation. It's a great pleasure to be here again. Okay, so this is joint work with Changdu. Doesn't work here. From Penn State, and my former PhD student Yanzhi Zhang, who is a tenure-track assistant professor at Missouri University of Science and Technology, and Dr. Alexander Klein and Dieter Yaksh, they are physicists from Oxford, and my current students, Qinlin Tang. Okay, a brief outline. So first, I'd like to say what's the means of quantized vortices in superconducting superfluidity, and the mathematical model I want to study. Then, how to find the central vortex states and their stability. Then, so vortex interaction. For this kind of vortex interaction, the PDE people can derive ODE system to model the motion of the vortex center with a nonlinear ODE system. We can solve this ODE system for several special cases, which give you quantitatively dynamical phenomena. And then numerical methods and the numerical results for this vortex interaction in whole space with potential and in bounded domain. Finally, a conclusion. Okay, so this quantized vortices is kind of a particle-like topological defect. Suppose you have a scalar field like psi with a complex function, can be wave function, can be outer parameter. Well, at the vortex center means at the center, say x0. So the wave function, the scale of the function is 0. If you use the fluid language, then at the vortex center, it's a vacuum. Well, if it's near the vortex center, so locally, if x0 is the vortex center, then psi at x0 equals 0. And near x0, if we express psi x equals square root of rho times exponential I phi, then any curve gamma includes this x0. The integral over this gamma d, so-called d phi is equal to 2 pi n. Well, n is an integer, so n is called index or circulation or winding number. So basically, that means for locally, the phase, if you go around, there's a jump. Or if you use fluid language, the velocity, the density is continuous, but the velocity has a jump near the center. So this kind of vortices are called the K phenomena of the superfluidity. It's the ability to support the disciplinaries flow. So you can observe like in superconductivity, like a triangle lattices, or like in Bose condensation. You can see each hole is a vortex. Okay, so this kind of exists like a superconductor. The model is Ginzburg-Landau equations. Or in liquid helium 3 or 4, either using two fluid model with a coupled Euler system. So you have a density, velocity, for normal part for superfluid part. Or you can use a Gross-Place equation to model quantum fluids, quantum phenomena. Or in Bose condensation, so like a nonlinear Schrödinger equation or GPE. Or in nonlinear optics, or like propagation of laser beam, like a nonlinear Schrödinger equation or nonlinear wave equation. So this is a typical experimental result. Like here has a giant vortex. You can see inside here the domain, the density is almost 0. Here is a vortex lattice observed in experiments. Okay, so today I like to study the following models. One is the scalar Ginzburg-Landau equation for superconductors or nonlinear Gator flow. So here is dt psi equals this one here, and so here psi is complex vector function, and the Gross-Place equation for nonlinear optics or for BEC or for superfluids. So the difference here is dt, here is minus I dt. So if you let here, you let t equal minus I tau, you get the same equation. So one is called the real time, one called imaginary time, something like that. Or nonlinear wave equation. Here is the signal derivative dtt psi. So here psi is a complex value wave function or order parameter. Like depends on how far field, like this potential v. If v is so called if psi, so the L2 number is fixed, finite, then you can see this psi is a wave function. Other if psi, see at the far field go to constant, then we see is order parameter. Here we have parameter epsilon is a fixed number, can be equal 1, can be very small. Okay, potential V is a real value external potential. So you can see in these three equations, the right-hand side are the same. Okay, so if we introduce this is called free energy or Lyapunov functional, this is the kinetic part, the potential part, and the interaction part. So then you can say that for GPE equation, you can write it as minus I d psi dt equal this one. So this immediately implies that the energy is conserved, and also density is conserved, something like this one. So for this equation, so this kind of dispersive equation. So if in 1D it admits like admits particle-like solutions. In 1D like a soliton, in 2D so the kinks or vortices. If for Ginzburg-Landau equation written as d psi dt equal this one, so it's kind of easy to show that here psi star is a kind of psi. So this equation is energy diminished. Okay, so there are two kinds of vortices. One we call bright tail vortices. We borrow the bright soliton, dark soliton. So this is for the Ginzburg-Landau equation or GP or nonlinear wave equation. So here psi is order parameter. The setup is the following. We assume the potential V equal 1 at the far field. That means the background you have a uniform, like a superfluids or superconductors. And then we require psi, the density of the epsilon psi goes to 1 at the far field. For example, psi goes to exponential minus I, or exponential I m theta. Here, r theta is polar coordinates. So, the business to start this kind of setup starts from John New from 1990s. So he first considers the time independent case. You can see in this equation, if you let d psi dt equals 0, you get the right hand side the same. So you get the same time independent equation. Okay, so then we consider so we know the equation admits the constant psi equal exponential I theta 0 is a solution. That's trivial solution. An interesting solution is called a vortex solution. So we find the solution psi equal phi n of x, where equal fn r exponential I n theta. Here r theta is polar coordinates. So you plug this ansatz into the equation, right hand side in the previous equation, and let t equals the time interval equation. We end up with ODE, second order ODE for fn r equals this one, and at the origin we need to require this fn is continuous. So we know the exponential I n theta is not continuous, so we need to require fn 0 equals 0. And at the far field, since psi goes to 1, so we need to require fn at the infinite goes to 1. So for this standard ODE, nonlinear ODE, you can do asymptotics. When r goes to 0, fn r is equal a constant a times r to the power to the absolute value n. And at the far field, the solution fn r goes to 1 minus n squared over 2r squared. That means at the origin, the increase polynomially. But at far field, the leading order constant, next order decrease at the next order is order 1 over r squared. So polynomial decay. Okay, this is a numerical solution. This is r, this is fn r. For n equal 1 is solid line. For n equal 2 is this one. And n equals 3. So you can see this is the cost size will increase with this 1D number increases. This is a phase. You can see this n equal 1 is a phase. So this plot is the epsilon psi. You can see it's equal 1 at the far field, at the x equal at the origin it's 0. So there's like a hole inside. So if you do a cutoff, see if this is the x-axis, right? The solution looks one almost parallel, something like this one. Okay, this is the red hill for n equal 1. This n equal 5. This is a phase. Yes, n equal 1. The phase when you go see that from 0 to 2 pi, the 2 pi jump. It's n equal 5, you have 10 pi jump. Okay. Another we call dark tail vortices. This is like in BEC. See here, psi is a wave function. Since here we have the equation can be written as I dt psi equal minus Laplacian psi plus x squared over 2 psi. So here we have a confinement v of x equal x squared over 2. So when x go to infinite, v of x go to infinite. So in this case, we know the psi square is a wave function. So as atomic number equal 1. So then we plug psi x t equal exponential minus I mu n t phi n x. In fact, previously you can think this mu n equals 0. Here, this mu n is non-zero. If mu n equals 0, there are no solution. So mu is non-zero, and phi n x equal fn r exponential I n theta. So you plug this ansatz into this equation. You end up with kind of a nonlinear eigenvalue problem for mu n and phi fn. So here you need to find a mu n and fn together. So this one and fn 0 equals 0 and fn infinity equals 0. And also have this normalization condition. For this one, you can also do asymptotics. When r equals 0, it's the same as previously. That means what is cos size is similar. But at far field, the fnr equal b times r to the power n epsilon n exponential minus r squared. So for this solution at a far field, the decay exponential fast. So somehow like this one. Something like this one. Okay, so this two we call two kinds of these vortices. From analysis point of view, the first one is easy to analysis since the cos size is order 1, but the support of the solution is infinite. So there's a clear scale separation. But for this case, the cos size is order 1. The typical support of the solution is same order. There are no scale separation. So this from analysis, if you want to study what is center, or what is how motion, you do asymptotics. This is easier. This is harder. Well, for computation, this is easier. This since at far field solution take to exponential fast, you can truncate on box. But this guy is much harder because the solution is non-zero at far field. Okay, so this is a dark soliton, a dark tail vortices. You can say here this is R, this is F and R. The n equal 1 is solid line, n equal 2 is something here. Again, the cos size is increased, but the same order. So this is the epsilon psi. You can say the 0 at far field, but the increase then decrease to 0 and increase again. Sometimes it cos. This is the phase. So the phase is similar. And here, this is n equal 1, this is n equal 5. For this dark tail vortices. This is in 3D called dark tail vortice line in 3D. You can say here this is at the surface plot of the density. You can see there vortice line at the z-axis. Here is n equal 1, n equal 5. Basically, when the number large, the cos size is increased. So when we have this kind of vortice states, so we want to start like a dynamic stability or so dynamic law. First of all, people interested with dynamic stability. So from what I know, for Ginzburg-Landau equation, people can prove some kind of stability analysis. But for GP equation, they always make assumption. All PDE people assume this n equal when the number n equal 1 or minus 1, it is dynamically stable. While n bigger than 1, the epsilon of n bigger than 1 is unstable. So here I give a numerical evidence. So what we do is we choose epsilon equal 1, we choose v of xt equal 1, and we choose percent 0 is f phi and h. This is solved numerically for the ODE. Then plus a noise for some kind of perturbation. Then for Ginzburg-Landau or linear wave equation, so for n equal 1, so what here I plot is the density. So what here I plot is, you can see is minus epsilon of n psi. N equal 1. You can see here I have two pills, and this is a perturbation. But then when time evolves for Ginzburg-Landau equation, you can see when time evolves, this perturbation disappear due to this kind of dissipative system. So the leftover is a one-D number n equal 1 vortices. However, if n equals 3, again this is minus epsilon psi. So the basically here is 1, here is 0, this here is 1. But I just like want to see the motion in the center, so I up and down. Okay, you can see again here I do a small, still do a small perturbation. You can see the vortex split to 3 vortices. Of course, the splitting pattern depends on your perturbation. You can see after basically a long time later, if n equals 3, you split to 3 vortices with one number n equal 1. Then for Schrödinger equation, for Schrödinger equation, if you do perturbation at the initial data, then you will say no matter n equal 1 or 5, this is stable. However, if you do a small perturbation at the potential, that means here if you perturb this vxt to plus a wxt for this short time, then you will see, you can see this is for Schrödinger equation or GP equation, n equal 1. Here I do a perturbation at the potential. You can see somehow apply a potential at say 1 point. You can see after some time, well, for like from t equal 0 to pi. You can see after t equal pi, no perturbation at the potential. You can see all the perturbation radiate out to infinite. Because for this, you can see afterwards, because after you remove the perturbation, the system is mass conservation, energy conservation. But the perturbed part will radiate out to infinite. So left over is again as a n equal 1 vortices. Then if n equals 3, you can see, so we do a small perturbation. After some time, you can see the vortex, split to 3 vortices. But here you can see the vortex core, they are, overlapped. You cannot like Gibbs-Blandau equation, they separate very quickly, well separated 3 vortices. But here you have 3. You can see origin is 1 vortices at the origin, n equal one number n equals 3. But now it's become 3 vortices, but each one is n equal 1. So basically, on this kind of study, we have the following conclusion. So for Gibbs-Blandau equation or nonlinear wave equation, under perturbation either in initial data or in expanded potential, n equal 1 or minus 1 is dynamically stable. Well, if epsilon of n bigger than 1, it's dynamically unstable. So the splitting pattern depends on the perturbation. So, but however, when t much bigger than 1, it becomes n well separated vortices with one number n equal 1 or minus 1. Because if initial n bigger than 0, you split to n one number n equal 1 vortices. If initial n like equal minus 5, you split it to 5 vortices with one number n equal minus 1. Similarly, for Schrödinger equation or Gibbs-Blandau, the Gross-Peterson equation, if you do under perturbation in initial data, this for no matter which n it is, the dynamically stable. Because here we can easily to show that the angular momentum expectation, because here my v equal 1, which is uniform or is radial symmetric. So we can show that the angular momentum expectation is conserved. So they cannot split. However, if you do a perturbation in external potential, then for n equal plus or minus 1, dynamically stable. And if epsilon of n bigger than 1, dynamically unstable, but the vortices center cannot move out of the core size. Just they overlapped for a long time. Okay, so after we have this, now we know for Gibbs-Blandau equation or in superfluids or superconductivities, the vortex, when quantum vortices, if n equal plus or minus 1, is dynamically stable. Then if n bigger, epsilon n bigger than 1, is unstable. So people are interested in the interaction. Of course, the interaction is for n equal plus or minus 1. So, well, if you want to study interaction, what's your initial setup? For this called the bright tail vortices, you just do is you choose the psi 0x equal the product of phi m g x minus x g 0. Well, this each phi m g x is a central vortices centered at the origin with one number mg. Mg is equal 1 or minus 1. So okay, then we shift to xg 0 position. That means initially we have like n vortices located at x10, x20, xn0. Okay, like here we have one vortex here, another one like here. You have to product because the far field is always 1. This kind of setup for this bright tail vortices. because the far field the density is 1, so you do product. So basically the cosine is just here. Okay, this is easy. However, for ductile vortices, there are 2 ways to set up the initial data. One way is if they are well separated, like this case here. This is one. This whatever I plot is I think is I think is minus. Okay, again it's minus absolute precise. You can say 0 everywhere, but at here is there's a what is here, what is here. That means if this two vertices, since here the support is finite, so if the distance between two vertices is far away, much bigger than the cosine, so they are well separated. You can use summation, right? Using using summation. Another way is we call the overlapped. That means we choose the precise r t equals 0 is alpha times this alpha make this precise s number is 1. Phi g precise gsr is the ground state of the problem, which is the no vortices. Then you times at each rg is a vortices. This is pq. So somehow like this one. So here we have we have a phi 1 of x. This is a one number with 1 vortices. This is equal f1r exponential I theta, right? Of course, we have a phi g of x. This is a ground state. This is roughly equal f0 of r. So what we do is this p of x is equal phi 1 of x over phi 0 x. This is basically what is called at the origin. Then we do multiply shift to the location at rg, the product. So here basically you can say we have a common common background of the ground state. Then you have your superposition here, one vortices. Superposition here, another vortices. Say superposition here, another vortices. Like some here. You do this something like this one. This was set up. So this way is easier. This way, because also you can also do like this way. But we talked to the physicist. They said this way experiment for ductile vortices. If you do this way, experiment is not easy to do. But for this kind of setup, you can first create a ground state, then do a perturbation. You can generate this kind of initial data. So when you do some physical problems, sometimes if you talk to physicists, they say, oh, this way mathematics is interesting, but physics cannot, produced. Okay. Then for ductile vortices, we have so if we start from this kind of initial data, then we say, how does the vortex center? Because at t equals 0, we know this xg is 0. When time evolves, the vortex center at xg t, how xg t the motion? Well, in physics, PDE people can get for brittle vortices, the far field is uniform background. You have for Ginsburg-Landau equation, they get kappa constant times vgt is the velocity. So the dxj dt, because xjt is the gs vortex center at the time t. So equal 2mg summation L equal 1 to n, L does not equal g. ml xj at t minus x is equal this one. This is initial data. This is for Ginsburg-Landau equation. This is for gross precision equation. So here, this is g, matrix g is simplex matrices. And for wave equation is a second order ODE. Somehow, this is PDP can derive. So basically, using this, suppose the vortex center are well separated, they using asymptotics derive this kind of ODE system. Well, now I want to ask from this ODE, this is fully linear ODE system. What does this ODE system tell us? So, and for this ODE system, PDP can say for simple case like if say for n equal 2. And say n equal 2 and just a pair of vortices. Also, what is a pair? That means the M1, the two vortices, both are 1, the same one number. So for Ginsburg-Landau equation or linear wave equation, they find that the pair of vortices with the same one number, index, and go repulsive, something like this one. And if opposite, then people call vortex dipole or vortex anti-vortices. they undergo so-called attractive interaction. This is by John New, a lot of people. Then, like Fan Hualin, they prove that the energy will be concentrated at the vortex in 2D and 3D filaments. And also later, like Chapman or like other people, if this V is not equal 1, but there's a local minimum. They show that if certain vortices, they go to the minimum position of V potential. For Schrödinger equation, again, they show that the vortices behave like a point vortex in ideal fluid. See, they always called they will absolutely go to 0. They always called the Kirchhoff law of fluid point vortices. And then later, by some so-called refined analysis, they found the equation for vortices the second order, and also find a radiation in the system. Well, here we try to show that for this ODE system, if your initial data is some special setup, we can solve this ODE system analytically, which give you sort of quantitatively the dynamic phenomena. So first we show that the mass center or the location center is conserved for Ginzburg-Landau equation. Then if we define x bar t equal xjt, because remember xjt is the position of the just vortices at time t. So the sum together, we can show that this x bar t for Ginzburg-Landau equation is conserved. For this nonlinear wave equation, well, it is conserved if initial the mean velocity is 0. Otherwise, they move to infinite. Because here is x bar t equal x bar 0 plus t times v bar 0 for wave equation, the second order ODE. Well, for GPE, we define so-called the signed mass center. So with x tilde t equal mg times xg. So remember, xg is a position, mg is a one-in number. Of course, if mg is the same, so this is of course same as the previous the mass center. But if mg there's some part is repulsive, some plus, some minus, you have this different. So for GPE, this guy is a conserved quantity. Okay, then also we can show that if you have any n vortices, n greater or equal to, the vortices with the same one number, but the initial liquidity on a circle uniformly. That means if xj0 equal a times cosine 2j pi over n sine 2j pi over n, and mj equal 1 or minus 1, the same. And then this a is constant. Okay. Then we can, for Ginzburg-Landau equation, we can find for the ODE system. Since with this kind of initial setup, we can try some ansatz for the nonlinear ODE based on our numerical solution. We can find this xjt equals this one. So this shows that the n vortices at time t is still on a circle, uniform located, but the distance is the radius of the circle is larger and larger. So this is the plot. You can say this two vortices, they go forward. This 3 and 4. Okay, for Ginzburg-Landau equation, or for this kind of dissipative equation. Well, for Schrödinger equation, and xjt equal a, well, they just rotate. You can say xjt equal a cosine 2j pi over n plus n minus 1 a squared times t. So just rotate. So here give you the plot. You can say this n equal 2. Initial 1 here, n equal 2. They rotate counterclockwise. And n equals 3, the same. But the rotation frequency or the angular velocity is different. Therefore, any n, this is the solution. Another case is if for any n greater equals 3, like vortices on a circle and its center. Let me have n minus 1 uniformly on a circle, but the last one at the center of the circle. Then again, due to the symmetry, the center one doesn't move, but the rest one they move. For Ginzburg-Landau equation, they move outwards. Here, give you a plot. You can see it's easier. So if I have 3 vortices, one at the origin, the other at the 1 and minus 1. So the origin one doesn't move, the other two move repulsively. Here, same. Well, for Schrödinger equation, you can see again the center one doesn't move. The rest on the circle they rotate counterclockwise. You can see here the origin one doesn't move. the initial position location. These two, they rotate. Here is for n equal 4 situation. Okay. So the next case is if two opposite vertices, that means initial x1 0 equal minus x2 0 equal this one, and m1 equal 1, m2 equal minus 1. So for the Ginzburg-Landau equation, this shows that the solution set this one. So this shows that the final time merge. So if t equal a square times kappa over 2, the xt equals 0. So something like this one. So these two guys, one here, plus 1 here, minus 1 here, they merge at the origin, at the center, at the final time. Well, if for Schrödinger equation, this shows that if solve this ODE, so they move parallel. You can say solution equals this one. If this gives you a figure shows, you can say the plus 1, minus 1, they move parallel. This shows that no matter what A it is, if the ODE is valid, this is the solution. Next one is maybe more interesting is you have suppose you have capital N, NaN, greater equals 3, opposite vertices on a circle and center. Suppose I have n minus 1 vertices, the uniform on a circle with the same one number, and the last one at the center is minus, opposite. Then again, due to symmetry, the center doesn't move, but the rest, this has a critical n equal 4. Oh, let me see. Yeah, n equal 4. You can say this shows that if the xjt solves the ODE system, xjt equals this one. This you can say if n equals 4. So this pattern is an equilibrium of the ODE system. That means in this solution, this setup, the water stays there. If the ODE is valid, the ODE system, the water center doesn't move. If n equals 3, they will merge. But n bigger than 4, like 5, 6, they move repulsively. So the n equals 4 is a critical case. That means if you have a positive and negative one, so n equals 3 plus minus, they merge. N equals 4 plus minus doesn't move. It becomes an equilibrium of the ODE system. Of course, this pattern is not stable. And n equals 5, you can say minus 4 plus. The positive one go outward. So here there also you have positive vertices and negative vertices. There's no collision. Similarly, for Schrödinger equation, the origin one doesn't move, the rest will move. Again here they rotate. But the interesting is again n equals 4 is critical. You can say if n equals 4, again equilibrium. And here is n equals 4, is this equals 0. But if n equals 3, they rotate clockwise. And n bigger than 4, they rotate counterclockwise. You can say here, the minus 1, n equals 3, minus 1 plus, they rotate clockwise. And n equals 4, minus 3 plus doesn't move. And n equals 5, minus 4 plus, they move counterclockwise. So different. Well, we can solve many other cases, but I don't want to show here. For many other cases you can find analytically. And also, interesting is like for Ginzburg-Landau Schrödinger equation for this ODE system, when the solution, the global solution, we know local solution is always local well closeness is fine, but whether for the ODE system given initial data, given the one number, whether there is a global solution. From our simulation, say for Ginzburg-Landau system, for Schrödinger system, there are no collision. So that means the ODE system, the solution exists globally. For this simulation, we can prove for several cases. Well, for Ginzburg-Landau equation, we know if they have opposite one numbers, they may collide, they may not collide. So is there a criteria you can from initial data or one number? Well, when the solution collision, because the collision means the right hand side equal infinite. Because one side has something, xjt minus xit over xjt minus xjt xit epsilon square. If these two vertices go to very close, the right hand side go to infinite. Okay, so now this is what we learn from this ODE system or reduced dynamic law. Well, of course, people ask, is this ODE system is leading order approximation? How good it is? Is this solution agree with the solution of the PDE? Qualitatively and quantitatively. Then we need to solve this PDE. As I said here, there's some numerical difficulties. We know the solution is better for this kind of relative vortices. If your n equals like 20, and the far field solution is psi goes to exponential I 20 theta. So solution in the transfer direction is highly oscillate. Okay, so previously people use like a find a difference or find an element using Cartesian grid. If you use Cartesian grid, all the solution in one direction smooth, the other direction oscillate. If you use Cartesian grid, everywhere you plot it. Well, what we do is also solution. If for this one solution is only quadratic decay, in the radial direction. That means when your solution, we solve it in the very large domain. Okay, and also it's nonlinear system. It's hard to design effective absorbing boundary condition. Also for Schrödinger equation, the solution is like a time reversible, time to invariant, and a dispersive equation. You need to try to keep so-called the conservation laws in this level. Also, you'll see the solution has a radiation. Although in R direction it's smooth initially, but at some time there's some small sound wave is generated, so which cause some numerical difficulties. So what we do is for relative vortices, what we do is we first apply a time splitting technique to decouple the nonlinearity. So first solve a free Schrödinger equation or free Quantized equation with a nonlinearity. Then we solve the nonlinear ODE system. For this nonlinear ODE system, we can solve analytically. Then you couple them together. And also we adapt to the polar coordinate, which can resolve the solution in the transfer better, and also match the far field condition naturally. So in the transfer direction, we use a Fourier transform, and in the radial direction, we use like a second order, first order finite element of a difference method. Well, for ductile vortices, this is much easier. We can use like time splitting technique to decouple nonlinearity. We use a Fourier transform. We turn on a box. So first case we turn on a rectangle, very large disk, like the radius like equal 5,000. The second one you can get the solution take exponential fast. You do on a box. Also different potential. If potential like a v equal x squared over 2, you can use like a generalized Lager-Hermit polynomial, which is the eigenfunction of the linear operator to do it. I don't want to see detail here for the method. I just show some result. So first case we want to study what is dynamics and the interaction in 2 dimensions. Well, for 2, n equal 2, simple case. So here choose epsilon equal 1, v equal 1, uniform. And psi 0, x equals this one, and the far field psi goes to exponential mm theta, m equals the summation of this one. We choose n equal 2, and n1 equal 1, n2 equal 1, and x1 equal a0, x2 equal minus a0. For Quantized equation, you can see these two vertices. What I plot here is, minus epsilon psi. So this two top is the vertex center. This is 0, and the background is 1. Here is 1. So this vertices, these two guys, they move repulsively. You can see, and later we also trace the time evolution of the vertex center. They match the ODE system qualitatively. This is for Quantized. If for gross-potential equation, for dispersive equation, you can see again they're the same. When time evolve, these two guys rotate, like 2 persons are dancing. You can see they rotate. The center is almost on a circle, but the radius of the circle will increase with the time if you trace the vertex center. So if this is a trajectory, you can see this is a Quantized equation. Quantized equation, you can see this two vertex center initially one is 2 0 and minus 2 0. They increase. This is the distance between these two vertices, and we compare the solution of this one with the ODE system. They agree very well. However, for the gross potential equation, for this vertex pair, there are 2 stages. Initially, they have a very fast change initially to go to a vertex center or a radius. Then they rotate. Well, this radius of the circle will increase with time. This is the distance between these two vertices. You can see initially the distance is 4. One is 2, 0, one is minus 2, 0. They increase to like a 4.5 very quickly, and then we can see that the distance between these two vertices, the diameter of the circle is increased with time. This is time t, and you can measure this this increase, this rate. The rate is roughly is a0 plus t to the power 1/6, and this can be agree with the asymptotics analysis. For linear wave equation, they're similar as this the Gibbs-Landau equation. They have this motion. So we have some conclusion for this two vortices. For Gibbs-Landau equation, they undergo a repulsive interaction, something like this one. And the cosines of the two vortices will be well separated. And the energy will decrease. So basically, the energy, the E of psi will go to 2 times the E of psi 1, or phi 1. Phi 1 is the number 1 vortices at the origin, center vortex at the origin, at far field. For linear Schrödinger equation, they behave like a point vortex in ideal fluid. The two vortices center will move almost along a circle, but the radius of circle will increase very slowly. And we will see the energy conservation and the radiation. And for linear wave equation, the similar as observation can be for this Gibbs-Landau equation. In fact, for any vortices, they have similar pattern, like here. Okay, next case we study is because for two vortices with opposite winding number, we choose n equal 2, n1 equal 1, n2 equal minus 1. Then for Gibbs-Landau equation, again, you can see this is the density, the minus epsilon psi. This initially, these two vortices is the same as, the density is the same as the vortex pair. Here is what they call vortex antivortices or vortex dipole. Then these two guys, you can see an attractive interaction. The center go together, then they along a line, then they merge and disappear. So when t go to infinite, the outer prime psi go to exponential I star 0, go to constant. So this, the energy go to 0 due to this kind of dissipated system. Well, for Schrödinger equation, there are two scenarios. Case one is if the distance between two vortices are small compared to cosines. So if these two guys, they move along a parabolic line. So one here, say one here, they move. They move along a parabolic line, they merge at a finite time. You can see here, this is the merge. And then they go to far field, really to infinite. Well, in the other case, if the two vortices, they are well separate, then the distance between two vortices are much larger than the cosines. You can see these two vortices, they move almost parallel. And during the motion, there's a solitary wave is going along these vortices, the motion. If you look at the velocity field, so if the vortex distance are small, so what I plot here is, so you write psi equal square root of rho exponential I s. This is the grad of s, the quantum velocity. You can see one is one number plus 1 minus 1. These two guys, they move towards each other and perpendicularly go downwards, and then at finite time they merge, and then disappear. If here, if they are well separate, these two guys almost move parallel. You can see these two vertex centers move almost parallel. Okay, if you look at trajectory, for Gibbs-Landau equation, these two plus minus, they move together, the distance at equal 0 at finite time. Well, for Schrödinger equation or gross-potential equation, you can see if this is small, the center, they move along this parabolic line, they merge at finite time. Well, if the well separate, you can see this distance is move almost parallel. If you look at this, the distance between the two vertices, after some time, they're almost constant. For linear wave equation, similar as Gibbs-Landau equation. Oh, okay. Okay, we have some conclusion for this so-called vortex dipole interaction. So for Gibbs-Landau equation, or kind of dissipative equation, they undergo an attractive interaction and merge at finite time. So then the energy will go to 0 when t goes to infinite. For gross-potential equation, it depends on the initial distance of the two vortex center. If it's small, they merge at finite time and generate a shock wave at the velocity. And if it's large, they move almost parallel and don't merge, and their solitary wave is generated during the motion. And you can see the energy conservation and also situation. So this plot is, at some time for psi x0 t equals 20, t equals 10. You can see initially, you can see here a lot of sound wave is generated here, some radiation. You can observe from here and here. Also, there are sound wave generation here. For nonlinear wave equations, they undergo an attractive interaction and a more definite time, similar as for Gibbs-Landau equation. Okay, so this is if the background is uniform, v equal 1. However, if v like v equal x squared over 2, so for this non-uniform background, like in Bose condensation, or so in BC setup, or so the non-uniform background. So here, the things become much harder. Even for linear case, so if you v equal x squared over 2, no interaction. Then for n equal 1, you can find again you choose what I did set up for this overlapped initial data. You can see for v equal 1, this the two vertices move along a circle. So xvt equal x1 cos nt, yvt equal x1 sin t. That means initially you shift the vertex to initially at the center. You shift to x1 0. You have the motion along a circle. For what is a pair? For linear case, you get they move like a ellipse. And for what is dipole, they just we can derive all this kind of for this for linear case we can derive using sort of variational principle, some method to derive this kind of motion law. Like I think this is n equal. Say okay, I think n equal 2 is somehow like okay. What is pair? This is for what is pair. Somehow the distance. Some case is circle, some is parabola, and this is like at this point doesn't move. So then for non-uniform case, the analysis becomes much complicated. We can also do some simulation. This is for linear case. If we do weakly nonlinear case, then the interaction is very small. If for what is pair, they move like okay. This what I say is like this is the trajectory. So if one here, the other here. They move not a circle, but they move something like almost like a circle, but the distance they change periodically. If you do what is dipole, so if you have a plus or minus, what is it? One is here, one is here, one is the other side. So this is what is dipole. They go downwards, they merge. After they merge, another what is pair will be generated at the boundary of the condensate. That's like if one here, they merge, then another two, plus and minus generated here, then they go downwards and repeat this process. Then if you have what is triple, that means if initially you have three vertices, one plus here, one minus here. Then this three vertices, the interaction, if you do simulation, we can count how many vertices at time t. So here, give a plot, you can see the vertex number, this is t, this vertex number. So initially you have 3, and sometimes you have 2, you have 1. Then sometimes you have 5. So here you can see if initially you have 3, and sometimes the 2 or what is paired, they merge, disappear, left 1. Then another time, another 2 vertex pair with what is dipole are generated. You get a 5, something like that. So you can see at some stage there are 5 vertices during the simulation. So here, even with what is number is not conserved. They can. This only shows that if the confinement is and the radial symmetric. So either a pair, a dipole, or what is an antiphase disappear together, or they generate together, something like that. So of course, for strong interaction, much complicated phenomena. Even for weak interaction case, no reduced dynamic law at the moment. Of course, pure interest to see. Okay. So here I like to show some so-called what is interaction on bounded domain. Well, there the boundary condition will generate a lot of interesting phenomena. So here we consider the Gibbs-Landau equation or Schrödinger equation on a bounded domain. Of course, there are 3 different boundary conditions. See, in domain omega, where you have a dielectric boundary condition, you have a Neumann boundary condition, or you can have a periodic boundary condition. Well, so here the hard problem is how to choose a proper initial data which satisfies the boundary condition. Otherwise, you have initial layer and layer boundary. So what we do is for this data boundary condition, we know for data boundary what you choose is something like what you have is we say psi goes to a boundary say equal g. Of course, you require this g equal 1, right? Again, what we do is we choose psi 0 of x equal a product of phi nj x minus xj 0 and j equal 1 to capital N. Well, this phi n x again equal f n r exponential I n theta. Well, this f and r now is something like this one. So this is r, this is my f and r. It's equal 0 here, increase polynomial at something like here, then goes to some 1 here. Then so this is capital R. So after capital R, this f is always 1. If using this kind of setup, the boundary condition, so this guy is up because we need to shift. As long as you choose this is large enough, you do a shift, the boundary is still always 1. So when you do product, it's still satisfied. And then another case is here, this one, then times exponential I hx. This hx is a so-called a harmonic function. Then you see this h will affect the dynamics. In fact, for this case, PD people also have so-called the ODE system, and they also see the boundary effect. This is for data boundary condition. For non-boundary condition, what we do is we choose here as polynomial, here the equal 1 for regime, then the letter it goes down 0, then equal 0 in this regime. This is, this is always 0. So when we choose this way, you do a shift, and the boundary is always 0. So essentially, this if you do this non-boundary condition d psi dn, okay, at the boundary of omega equals 0. So what we choose is choose f and r, something like in this set. So this part is always 0. Then it satisfies this part. Okay, so here just show due to time just show this the gross potential equation for superfluid. If with the data boundary condition on a disk, you can see what happens. If for what is pair, what I plot here is the contour plot of the density. You can see this is the yellow is 1 and the blue is 0. The what is center. Okay, so we do interaction. Again, these two guys they rotate, and here we can here due to a boundary domain, no boundary condition issue. So we can measure the dynamics and compare with the ODE system. They agree very well. However, if this is for what is dipole, so a plus and minus. So you can see these guys, they move almost parallel. But however, when they reach the boundary, due to this boundary is a circle, is a curved circle, right? But this becomes smaller and smaller. Then they merge, they disappear. Then you can see a lot of waves are generated, and like a sound wave. So this is the boundary domain problem. We can observe this sound wave generation, radiation very effectively. Because for whole space, because while you have some truncation, you need some boundary condition issue. Here, for this boundary domain, you can observe this phenomena very, very clearly. Okay, if for non-boundary condition, we have again we have for what is pair. Okay, now it's a non-boundary condition. You can see here initially we have it's on domain on rectangle. So you can see much harder, complicated general solution. You can see let me split to different pieces. I think all this part is not vortices. So I think this vortices I think still here. For this vortex dipole, for this vortex what is the pair? But for what's dipole? Again, you can see here the common domain is a rectangle because I use as what I said here, at the boundary is 0, right? So it satisfies d psi dn equal 0. So then you can see these two vortices dipole, they move downwards, almost parallel. Well, at some stage, they merge. Then due to non-boundary condition, homogeneous, the mass conservation, energy conservation. So you can see there are some radiation from boundary, there's sound wave generated. So here, this is just the result from 2 weeks ago. We don't compare OD very qualitatively, but quantitatively the agree seems very well. Also, we did some solutions for bounded domain for like Gibbs-Landau equation for superconductivities. I don't want to show here the similar phenomena. Because for bounded domain, things become much more complicated because the boundary effects, the radiation, comes in. A brief conclusion. So what we did here is for the reduced dynamic law or nonlinear OD system, different type. We show that for Gibbs-Landau equation, the mass center is conserved, and this for gross-potential equation, the sign mass center is conserved. Well, for a few types of initial data, we can solve the system analytically. And also we can have some partial results on the well-posedness or globality of the system. Then we do the numerical results. We study the Gibbs-Landau equation, the gross-potential equation, nonlinear wave equation, numerically for the West dynamics, because stability of vortices with different Random number. The conclusion is for n equal 1 minus 1 is dynamic stable, and the epsilon of n bigger than 1, dynamic unstable. Then we study interaction of what is pair, what is dipole, or what is triple, and much more. And we also carry out a study for what is dynamics and non-uniform potential, like in BEC or in other cases. And also we study what is interaction and unbounded domain with different boundary conditions, like Dirichlet, Neumann, and boundary effect. Okay, in the future we try to study this what is dynamics in Gibbs-Landau Schrödinger equation with external magnetic field and some other issues, also in 3 dimensions. If in 3 dimensions you have what is line, you have what is ring, and all other issues. Okay, I think I'll stop here, and thank you for your attention.
So, questions?
Yes.
When you talk about the numerical difficulties for simulation, you talk about the radiation.
Yes.
But I cannot catch up with the meaning of this.
Well, basically, solution initially smooth.
Yeah.
When time evolves, there's a lot of sound wave. It goes outwards. They call radiation. So the whole problem, the energy is conserved. But when you do so, you solve numerically. If you look at the energy inside a small domain, the energy will change. The energy will radiate out of this center. If you look at my solution, you can see. I think in one slide. Let me see. I think in one slide. Okay. Yeah, you can see here. So initial source also, you can see a lot of sound wave. This location will goes outwards. So they call sound radiation goes up.
So your discretizing should capture this.
Yeah, your scheme, should capture this. The solution capture this small scale. Otherwise, the problem.
But
for Gibbs-Landau equation, no this radiation. Only for gross-potential equation, the solution has this radiation.
But what's the difference between with the high oscillatory waves, because they are always oscillations?
Well, here you don't. If you small fixture epsilon, there are no high oscillation.
Right.
But after some time, due to this linear system, this some like a resonance of this radiation is generated during dynamics, not initial data.
The second question is, since you give many interesting stories about the boundaries effects to the solutions, but do you have any physical motivation for this?
Well, yeah, in experiment always bounded domain.
Yeah,
In
right.
physics, many cases bounded domain. Mathematicians of physics at the beginning don't know how to set a boundary condition. We just say first it's a whole space problem.
But not for gross-potential.
Okay.
For
Yeah.
the Gibbs.
People are not European study is bounded domain. Yeah. Yes.
Which boundary condition is physical, the Dirichlet or the Neumann?
Both are physical.
When is the Neumann? What does it mean, the Neumann boundary?
Let me see. Okay. If you apply the magnetic field, you have this kind of Gaussian boundary condition, which roughly corresponds to this Neumann boundary condition. Yes.
So in these latter examples that you showed, the simulation of GP
Yeah.
and bounded domains, what was the potential?
Well, here potential we choose 1. We don't choose.
Only one?
Yeah, we choose potential equal 1. For
Why did
GP.
you choose other potentials?
What we just here we just we study method. We choose 3 types like Dirichlet, Neumann, and also different cases, and also periodic. For of course, different boundary condition, the motion are completely different. Like for different boundary condition, you have this problem. You have, if after different boundary condition, even for different boundary condition, you can choose different h. If you choose h equals 0, and h say like h h equal another function. The PDP said, well, the solution will go to the face of h, the middle point of h along the circle, along the boundary. You will see if different h, the motion is different. For example, if h equals 0, it just move repulsively. But if you have h equal 2x plus 3y, they move something like this something different pattern. So this h, the boundary effect, will.
Sorry, I'm not following exactly.
Mm-hmm.
The question was about the external potential
Yeah.
in the Grotowski equation. How is it related to h?
Well, so here, for the boundary domain, first we study h potential equal 1. This uniform for boundary domain. Of course, you can choose the potential another function like say 1 over 1 plus x squared or some other functions. Yeah, numerical no difficulty. But of course, we always choose v equal 1 because for v equal 1, there is reduced dynamic law. We can compare the solution from PDE to this ODE system to see how good this reduced dynamic law in boundary domain. Because in boundary domain, the ODE system will incorporate this boundary effect into the ODE system.
So maybe further discussions postponed to the break.
No.
Let's thank the speaker again.